Hello students, welcome to Talk on Civil Engineering. So let us see what are the stresses that will come in rigid pavement or the cement concrete pavements or cement concrete slabs that are laid over the subgrade. Okay. So the analysis part for the stresses in rigid pavement is given by HM Westergaard. Is the first scientist who gave analyzing part or analyzing procedure for the rigid pavements. So for calculating the stresses in rigid pavement also, we are going to use the equations that are provided by the Westergaard itself. What he assumed is the pressure that is applied over the slab. The pressure that is applied over the slab is directly proportional to the deflections. And he said that what are the deflections that are occurred in the slab, they are inducing the deformation, the same deformations in the subgrade. So the deformations in the subgrade is proportional to the deflections in the slab, and this deflection in the slab is proportional to the pressure. Okay, so he gave equation that P is proportional to the deflections and P is equal to K into delta. So here K is nothing but the modulus of subgrade reaction. So here K is modulus of subgrade. So based on this concept, he has provided a number of equations to calculate stresses at different conditions, right? So now let us see what are the stresses in rigid pavement and how we are going to calculate that, or what are the equations that Westergaard is provided to calculate the stress in rigid pavement, stresses in rigid pavement. So here you will have three types of stresses. You will get three types of stresses. One, due to wheel load. And the second one, so this is the first one, and second one is due to the temperature variation, or due to the temperature change. So you get stresses like warping stresses will be there. And the third one, the frictional stresses. So these are the three stresses we need to find in rigid pavements. Now coming to stress due to wheel load. So Westergaard is provided the equations to find out the stresses due to wheel load and for warping stresses also at different portions. Firstly, let us see what are the different portions in the slab or rigid pavement. So if this is a rigid pavement, so these are the edges. So this is edges. And these are the corners. And this is the interior part. Okay, that means at three different portions, the stress equations are provided by the Westergaard. Okay, that is edge, interior, and corner. Now let us see what are the equations. So stress at edges, the equation provided is sigma E is equal to 0.572 P divided by H square 4 log L by B plus 0.359. Okay, so this is equation to calculate stress at edge. And coming to stress at interior, 0.316 P by H square 4 log L by B plus 1.069. And coming to stress at corner, sigma C 3P by H square 1 minus A root 2 by L to the power of 0.6. Okay, so here P is the wheel load. P is the wheel load in kgs, and H is a thickness of slab in centimeters. And what else? L. Here L is a radius of relative stiffness. Radius of relative stiffness. So this is also will be in centimeters. So A is the radius of contact area, or radius of loaded area, one and same. So this is also will be in centimeters. And B will be the radius of resisting area. So this is also will be in centimeters. Okay. Generally, this B value depends on A by H ratio. If A by H ratio is greater than 1.724, then your B will be equal to A. Okay. If this A by H is less than 1.724, then again Westergaard provided an equation to calculate B value, that B is equal to 1.6 A square plus H square minus 0.675 H. Okay. So these are the equations to calculate stresses due to wheel load. At various portions, that is at edge, interior, and corner portions. Okay. Now let us see what are the equations that are provided by Westergaard for temperature change, the stresses due to temperature change or temperature variation. So that are called as warping stresses. So here also you will have stress at edge, stress at interior, and stress at corner. So now let us see the stress due to this temperature variation at edge. So that is equal to Cx E alpha T by 2 or Cy E alpha T by 2. So from these two equations, whichever is greater, that value will be used. So whichever is higher, so that value will be the stress due to temperature variation at edge. Okay. Now stress at interior due to temperature variation is equal to E alpha T divided by 2 Cx plus nu into Cy divided by 1 minus nu square. Okay. And coming to stress at corner due to temperature variation is equal to E alpha T divided by 3 1 minus nu into under root A by L. Okay. Here E will be, we know this is Young's modulus or modulus of elasticity of cement concrete, and alpha is the coefficient of thermal expansion. Okay, so this is the coefficient of thermal expansion, and T is the temperature variation or difference in temperature. Or the temperature variation. And what else? Nu is a Poisson's ratio of cement concrete. And what else there? A is just similar, radius of contact area, and L is also the same, the radius of relative stiffness. And here you have Cx and Cy, right? So the Cx and Cy are So these are the coefficient of warping stresses. So our coefficients for the warping stresses, and these values you will get from a graph provided by the Westergaard. I will show the graph also, and this graph depends on Lx by L and Ly by L ratios. You will get the Cx and Cy. Okay, I will show that. So here, this is the warping stress coefficient graph provided by the Westergaard. So using this graph, we can calculate what is the Cx and Cy. Okay, for suppose if you got a Lx by Ly ratio, this Lx and Ly is nothing but, if this is your pavement, rigid pavement, you will have lateral joints and the longitudinal joints, right? So here These are called as longitudinal joints, and these are called as lateral joints. Okay, so the spacing of these lateral joints, that means this one, so this will be Lx. Okay, or the length of the slab along in the longitudinal direction will be Lx, and the length in lateral direction will be your Ly. So that means the spacing of the longitudinal joints. So this is longitudinal joint and this is lateral joint. Okay, and L is the same, the radius of relative stiffness. And suppose if you got Lx and Ly value around 10, so just you will so Lx, Ly, these are the Lx and Ly values. So Lx divided by L is 10. So this line you have to take, and it is intersecting the curve at here. So that means your Cx value will be one slightly above that value, that is maybe 1.03. Okay, so like that, using this graph, we are going to calculate Cx and Cy. Yeah. So I hope it is clear. So you need to memorize these equations to find out the stresses or the warping stresses or stresses due to temperature change. Okay, for rigid pavements. Right now, let us see the stress due to frictional stresses or due to friction between the lower portion of the slab and the upper layer of the subgrade. Okay, so because usually the slab due to the temperature variation, the expansion will be happening and the contraction will be happening. So because of this movement, there will be some frictional stresses developed at the contact portion of the subgrade and the cement concrete slab. Okay, so in order to find out the stresses because of this, sigma F, that is the frictional stresses in rigid pavement, is equal to F into L W by 2 into 10 to the power of 4. So we can use this equation to find out what is the stresses or what are the frictional stresses in the rigid pavement, the bottom portion of the slab and the top layer of subgrade. Okay, so here F is nothing but your frictional coefficient of friction, and L is the length of slab, and here W is the unit weight of cement concrete. Okay, the units will be the same. Like if whatever the units of unit weight, the same units should be used for the L also. Okay, so if the units are kg per centimeter cube here, then the L should be in centimeters. Using these equations, we are going to calculate the stresses. So have a snap. Thank you all.